We're continuing with polar coordinates, and this time surface area, but not surface area in general, just with rotating a curve about the x or y axis. Okay, so I wrote that. It's just of a curve rotated about the x or y axis, and I'm going to borrow a sketch. I borrowed the diagram from Parametric, and I'm going to modify it to work for polar coordinates, which is a little bit similar to Parametric. Instead of t, we're going to have theta. We're not going to have x and y directly in terms of theta, only indirectly, so out that goes. The setup will be that we'll be given r as a function of theta. I'll just move this up. Theta will go from alpha to beta, and as before, we'll assume that as it does that the curve is traversed only once, not back and forth or round and round. And indirectly, we have x and y in terms of theta, because x is r cosine theta still, and y is r sine theta. But instead of r, of course, we could put f of theta. So in a way, x and y are functions of theta. I won't show you the intermediate steps. I'll just erase these formulas. And I brought in the formula for arc length, because if you remember the formula for arc length, it will be very similar to the formula for surface area of rotation. So let's see. About the x-axis, what we'll get is instead of this, instead of L, we'll have an S. And what we'll have is the integral also from alpha to beta. We'll have a 2 pi in front, and in this case we'll have a y times the same thing as here. And I just copied this from here. So essentially the difference between this and this is the 2 pi y. Sometimes the 2 pi is written inside, doesn't matter. The idea is that this bit here with d theta is a little piece of the curve, and what we do is when we rotate it around the x-axis, we multiply by the circumference, which is 2 pi y. Of course, afterwards we have to substitute y from here and r from here, and we'll show that in the example. Let me just get to the equivalent with rotation about the y-axis. We use the same idea. We also have the integral from alpha to beta, but this time we're rotating around the y-axis, so if we have a little piece of curve and we multiply by the circumference is going to be 2 pi x, and then the same thing from here, like so. And I don't need this anymore. A remark on notation, in case you look on the internet, you will sometimes see that this bit here is called ds. So if I call this ds, and I don't want to get into all the reasons why ds, then these two formulas have a simpler expression. And I also want to bring in the formula for arc length. Here that is. So all these formulas can become simplified. This one becomes s equals 2 pi times the integral from alpha to beta of y ds. This one becomes s equals 2 pi times the integral from alpha to beta of x ds. And this one becomes L equals the integral from alpha to beta of ds. And this is just in case you encounter in other places the concept of ds. And like I said, some places the 2 pi is written inside, it could be outside, it doesn't really matter. So if you just remember the ds, and all the other formulas are easier to remember in case you don't get a formula sheet. Okay. So now I'll do one example each of rotation about the x-axis or the y-axis. So for exercise 1, I'm given the curve r equals 5 minus 4 sine theta, and I'm given it in the range where theta goes from 0 to pi. And I wrote out the problem that we have to just set up or express the integral, not to evaluate it, the integral that gives the surface area of this curve when it's rotated about the x-axis, so we need to use this formula. The reason it says we don't usually evaluate is the problems, the integrals come out so difficult, and we're not here to teach how to do integrals, just how to set it up. Okay, so I'm going to use this formula for the rotation about the x-axis, and let's see. Oh yeah, and I forgot to mention, we can assume that the curve is traced out exactly once. Don't have to prove that. So I need to get all the bits and pieces. If we use this formula, well, we still need r, and we need dr over d theta. So let's just write everything out. We have that r that was given is 5 minus 4 sine theta. Then we need dr over d theta. Dr over d theta is the derivative of this, which is just minus 4 cosine theta. And then we'll need also y, and y, which is r sine theta, is actually equal to, if I replace r with what it originally is here, is 5 minus 4 sine theta sine theta. And of course this is the alpha and this is the beta. So what we get, just get some more space here, is we get that s is 2 pi times the integral from 0 to pi of, now I can use this form here, y, which is this thing here, 5 minus 4 sine theta sine theta, and then the square root of r squared, which is 5 minus 4 sine theta squared, plus dr over d theta squared. I don't need the minus. I can just take 4 cosine theta squared, and then all this d theta. Now, yeah, this is an expression, and it does answer the question, but we want to simplify it a bit, if not evaluate it. I don't want to drag everything with me. Just the bit under the square root sign can be simplified. And I'll do that at the side. What we get is from here, using the formula for a minus b squared. It's a squared minus 2ab, 2 times 5 times 4 times sine theta, plus 4 squared sine squared theta, which is 16 sine squared theta. 5 squared is 25, and 2 times 5 times 4 is 40. But I still haven't taken the last bit, which is 4 squared, which is 16, and cosine squared theta. Now, the only thing that really simplifies is that because sine squared theta plus cosine squared theta is 1, this bit just comes out to be 16. So now I can rewrite this integral as equal to 2 pi, integral from 0 to pi. This part the same, 5 minus 4 sine theta times the square root of 25 plus 16 is 41, minus 40 sine theta, that's under the square root sign, this bit here, d theta, and that's one heck of an integral, and that's why you're not asked to evaluate it, just to express it. Okay, so that's an example of one type of rotation about the x-axis, And now let's do one about the y-axis.